Good afternoon, welcome back. So this is our 32nd lecture, and as always let me begin with a quick recap of what we did last time. So last time the title of the lecture was Gallagher Decoding Algorithm A and I began. So we are going to look at LDPC codes, and we are going to see how one can decode them by passing messages on the tanagraph that is associated to an LDPC code. So we have talked about the tanagraph earlier. So in this lecture, in the last lecture, we began by introducing message passing terminology, and here we said that O is the output alphabet of the channel, that is the alphabet whatever the channel provides you, whatever alphabet it uses, that is O. And then for the messages that are passed back and forth along the edges in the tanagraph, there is a common symbol, that is script M, and that is the message alphabet. Okay. And we assume that both alphabets are a subset of the real numbers. And similarly, at a check node, there are incoming messages that come in from the variable nodes and an outgoing message. And in general, if you consider these maps, each you can regard the operation that is conducted at each node as a map. So for example, initially the variable node map is just simply a map that carries a symbol from the output alphabet onto the message alphabet. In subsequent iterations, there are inputs from the check node. So in those situations, what the variable node puts out is a function of not just the channel output, but also the messages that are incoming from the other check nodes. At a check node, we just have incoming messages and a map from incoming to outgoing message. Now in our notation, we will put you reserve the superscript for the number of the iteration. Okay. So the 0th iteration, you have messages that go, you have a map that carries out maps from the channel output to the messages, and thereafter from these other maps here. And just to remind you quickly that the way our iterations go, we initially send messages from a variable to a check node, and at that point we start our iterations. So the first iteration begins on a check node, goes to the variable node and comes back. The second iteration does the same. Okay. So the iterations originate in a sense at the check nodes. There is a 0th iteration in which a message goes out from a variable node to a check node. So that is our terminology. And we are going to analyze the performance of these decoding algorithms, or rather we are going to actually analyze the performance of a class of decoding algorithms. Now these decoding algorithms have certain features in common. Actually they are required to for the purpose of making the analysis tractable, and one of the requirements is that supposing your incoming message from the channel is B times M, then your outgoing message is what it would have been in the absence of B times B itself, where B is a plus minus 1 symbol. Similarly, at a variable node, in the general case, if all the messages that are incoming, including the one that is incoming from the channel output, are all scaled by a factor B, then the output is also correspondingly scaled by the factor B. At a check node, if the incoming messages are scaled by different constants Bi, then the outgoing message is scaled by the product of these scale factors. Okay. So these are known as the variable and check node symmetry conditions. Okay. So I forgot to put that word in last time, so let me do that. Symmetry okay. Then in the middle of the lecture, I made a statement that we will now proceed to show that the number of incorrect messages passed along the edges of the tanagraph during each iteration is independent of the transmitted code word. But actually what we did was we deferred that. I think at a subsequent point I said let us defer that till a subsequent lecture. So, let me just make a note of it here, that this was deferred to lecture 32. All right. And then so after that I started discussing Gallagher's decoding algorithm A. So, Gallagher's decoding algorithm A says that initially the message that is passed on by a variable node is simply whatever comes in from the channel. Subsequently, it passes on whatever it receives from the channel unless it is overruled unanimously by all the other messages, okay, and that is explained by this. If the incoming is M0, then it is minus M0 if and only if all the other Mj disagree and say that it is minus M0, otherwise it is M0. And at a check node it is simply the product of the incoming messages. Now, Gallagher's algorithm assumes that we are dealing with a binary symmetric channel, and therefore, the channel output alphabet is plus minus 1, and you can see from the way these operations are defined that the message alphabet is also plus minus 1. So, so now at this point we understand the decoding algorithm. One question is, well, I understand that you are passing messages, how do you actually stop the algorithm and how do you make decisions? Well, what you actually do is you can stop after a prescribed number of iterations. Let us say that you stop after 20 iterations, and at that point what you do is you examine the messages that are outgoing along these edges leading from a variable node to a check node, and then you check for the sign of these messages. Now, these messages are either plus or minus 1 in the case of the Gallagher decoding algorithm. If and now keep another thing in mind, although we have not actually proven that and that is yet to be shown, it is the case that the performance analysis in terms of number of errors made in the decoding algorithm is actually independent of the transmitted code word. So, for the sake of convenience, what we will actually do is we will assume that the all one code word was actually transmitted. So, here given that the all one code word was transmitted, when you look at this tanagraph and you see a message that is going on the lth iteration from a variable node to a check node. Now, you should treat this message as an indication of what this node believes its value to be. So, since we are assuming that all these values are actually plus 1, okay. So, when I say all one code word, I mean the all one code word with reference to the alphabet which is plus minus 1. So, now if you look at the message on an edge and if it is negative, then that is in disagreement to its true value, because we already know that the true value is 1. For performance analysis, we assume that the all one code word was transmitted. So, that is what we mean by an incorrect message. So, when we speak of an incorrect message being sent over the tanagraph, what we mean is that the sign of the message that is transmitted along an edge in the tanagraph disagrees with the value plus 1 of the code symbol, which means that it is basically negative. All right. So, how does this algorithm perform? We will evaluate the performance by carrying out density evolution. This is a little bit more fancy a term than we need for the present. All that we mean is that we will estimate the number of incorrect messages passed during each iteration, and we will do this in iterative fashion. Okay. Again, so this is just to repeat, we are assuming, and let me emphasize here by writing this in red, we will assume that the all one code word was actually transmitted. Now, initially in the initial iteration, when you actually have so getting back here, initially you have a message that actually goes out from the variable node, and all that the variable node does is at this point it just simply passes on whatever it receives from the channel. Now, how correct or incorrect is that? The channel being binary symmetric, the probability that it actually sends an incorrect message, that it feeds an incorrect message to this node is 1 minus epsilon, is epsilon, sorry. So, the probability of an incorrect outgoing message is epsilon, and of correct is 1 minus epsilon. So, that in some sense kick starts the density evolution process. Okay. So, P0, so we use the following terminology. P01 means the probability that the message passed by a variable node during the 0th iteration is 1, okay, and similarly for this. And you can see that because it is the binary symmetric channel and this is the channel output, that P minus 1 is going to be epsilon, because we know that the actual transmitted code word is a 1. Now, in looking at this, you might wonder, well, how come you do not have any, this stands for iteration, this stands for the value of the code symbol, how come you do not have any notation that indicates a particular node? That is, you are passing messages in the tanagraph, how come your notation does not reflect which node I am transmitting out of? And the reason for that is because of symmetry. The probabilities will be the same because every node is operating under identical circumstances, because the input probabilities are epsilon 1 minus epsilon, or rather 1 minus epsilon epsilon for all the variable nodes. Okay. So, this is common. So, therefore, these are your initial probabilities, and these are used to jump start the iterative process. Then subsequently what happens? Okay. So, now the notation is that Q1 of L is the probability that on the Lth iteration the message that goes out from a check node to the variable node is actually a 1. Okay. So, we are talking about the probability that this particular message, that the message that is outgoing from a check node is actually either plus 1 or minus 1. And similarly for Q of minus 1. Then now we are going to do some calculations, and I brought this figure in here to explain those, but let us skip to the calculations and we will come back to this graph. So, what I actually said was that let us look at the probability that the message that is outgoing from a variable node is minus 1. Now, it is a minus 1 if and only if either the output from the channel is minus 1 and all the others are not unanimous in declaring it a 1, okay, which is represented by this term, or it is a 1 and the others are unanimous in declaring it a minus 1. Now, when I actually raise this to the power here, I am actually using independence, meaning that any, so let us take a look at the tanagraph here, or a segment of it. So, here this variable node is receiving a message from the channel and it is also receiving messages from the other check nodes. Now, and these messages are either plus or minus 1 with a certain probability, and the probability depends only on the channel realization, because there is no randomness anymore in the code word selection. We are assuming that the code word is all 1. Now, these messages are independent because each message here is an independent message. Why is that? Well, here is the computational tree which allows us to helps us understand that. Let us say you are passing a message from, let us say, a certain variable node to a check node. This message is a function of certain received symbols. So, now let us say that this is your first iteration. See, the 0th iteration is when variable nodes pass messages to check nodes. On the first iteration, the check node sends a message to the variable node and then back to the check node, and so on. Now, when we look at a message that is incoming to a variable node, like for example this one, this message here is purely a function. Let us say that on the second iteration, this message is purely a function of these received symbols. Likewise, this message here is purely a function of these received symbols. Therefore, these messages are independent, and this is what justifies this multiplication in the probability here. Okay. So, this was how you evolve from a q minus 1 L to a p minus 1 L. All right, and I think I am going to actually repeat this part of the derivation again. So, let me first of all copy this page. I am going to cut this page because we are going to carry it over to the next lecture. All right, and just as a recap, what we talked about is the alphabets arising in message passing. We also talked about independence assumptions. And then we began discussing Gallagher decoding rhythm A. Now, one other fact I should mention is that I think I mentioned this sometime earlier, that this density evolution analysis that we are actually carrying out assumes that you are operating with a Tanner graph which is tree like, which to depth 2L has a tree like neighborhood. That is, if you are carrying out 2 iterations, then to depth 4 it is a tree like neighborhood, which means that none of these variables actually repeat, because it is perfectly possible in the presence of cycles. For example, if this variable node here was the same as this variable node, that would indicate a cycle of length 8. So, we are assuming that up to depth 8 there are no up to length 8 there are no cycles, and which is the same as saying up to depth 4 there is no repeat symbols. Okay, so, we are assuming a tree like neighborhood. And now, I started out with a calculation. Let me just redo that. I think we may be able to do it in a simpler fashion today. So, we are now looking at a check node, and let me introduce some notation here. Let us say that the message that is actually being passed here is, so we already have a symbol for this, U1. So, maybe I should let me change that to something else here. Let us assume that these incoming messages are let us say mu 1 mu dc minus 1, and that the outgoing message is mu dc. And we know that each of these mu j's is either a plus 1 or a minus 1. We also know that Gallagher's decoding algorithm simply says that when you pass messages, you just at a check node you simply multiply the incoming messages, and that is how you compute your outgoing message. So, what that means is that therefore, mu dc is the product j is equal to 1 to dc minus 1 mu j. All right, and I want to carry this over to the next page. So, let us copy that. And now these are random variables, because the messages that are being passed are random variables, which are functions of the received variables. Okay, the randomness arises only because of the particular channel realization. So, let us take expectation on both sides. Therefore, the expected value of mu dc is the product j is equal to 1 to dc minus 1 expected value of mu j. Now, the probabilities of mu j, probability that mu j is equal to 1 in our notation, okay, because we are now talking about messages that are ingoing to a check node, is p l minus 1 1. Okay. And similarly, the probability that mu j is equal to minus 1 is p minus 1 l minus 1. So, since this is a plus minus 1 variable, since all the mu's are plus minus 1 variables, when you compute the expectation, so I will call this 1. Therefore, 1 gives us that, and I guess similarly, so I need to go back here again. So, these messages here are associated with probabilities p l minus 1 either plus or minus 1. Similarly, here this message over here is associated with probability q of l plus minus 1, because this is density evolution. Given densities of the incoming messages, you compute densities of the outgoing messages, and since iterations begin at check nodes, so you are going from the L minus 1th iteration to the Lth iteration. Okay, so that is the computation we are doing. So, in terms of expectation, it tells us that therefore q of L 1 minus q of minus 1 L is equal to p of 1 L minus 1 minus p of minus 1 L minus 1 raised to the power d sub c minus 1. Now, you raise it to a power because of the independence assumption, and instead of multiplying j minus 1 terms, you just have a single term, because all the densities along all the incoming messages are actually identical. Now, recognizing that of course, it is always true that if you add these two probabilities, you will get a 1. Therefore, it follows that 1 minus twice q minus 1 L is equal to 1 minus twice p minus 1 L minus 1 to the d c minus 1. Therefore, q minus 1 L is equal to 1 half of 1 minus 2 P minus 1, L minus 1, DC minus 1. Okay, so this is the expression that we end up with. All right. So we can now plug into the expression that we had earlier in the last lecture. So in the last lecture, which I am going to actually, let me copy over this page. So this is and remove some of the material that we don't need. Okay. So we actually have we have an expression for Q minus 1 of L in terms of P minus 1 of L minus 1, and now we have P minus 1 of L in terms of Q minus 1 of L. Okay, if we put the two together, so if I call this, let us say I call this 2, this is 2, and let me call this 3. Then from 2 and 3, from 2 and 3, we get that P minus 1 of L is equal to P minus 1 of 0 times 1 minus 1/2 of 1 plus 1 minus twice P minus 1 L minus 1 to the DC minus 1 dV minus 1 plus 1 minus P minus 1 0 of 1/2 1 minus twice P minus 1 L minus 1 to the DC minus 1 to the dV minus 1. I think let me just correct that. I think there is something not quite right here. Sorry about that. So this is half into 1 minus 2 P minus 1 L minus 1 DC minus 1. Okay. So we close this, raise this to the dV minus 1. So this is what we have, and that's what density. So this is the desired density evolution expression. Okay, so in density evolution, our aim is to actually find a recursive expression for the number of incorrect messages passed along each edge. So what we have actually done is we found out the probability that a message on a certain iteration, on the lth iteration, is incorrect, because -1 represents an incorrect message. After all, we assume that the one code word was transmitted. So, this is the probability of an incorrect message, and what we have been able to do is express it in terms of the initial channel probabilities, which are epsilon and 1 minus epsilon, which are known, and in terms of the corresponding probabilities in the previous iteration. So, that is what we actually wanted to do. Now, what you can actually, if you spend a little bit of time, you can show a couple of things. You can well, basically you can actually show that these probabilities at any iteration increase monotonically with increase in the channel crossover probability. That is one. And the second thing you can actually show is that as long as the channel probability is below a certain threshold, the probability of an incorrect message with increase in number of iterations goes to 0. The caveat is that we do assume that the neighborhood is tree like, okay, up to depth 12. So, if you are increasing the number of iterations, then we also assume that the neighborhood is tree like when we make this statement. So, let me just put that down. Can be shown that p minus 1 L increases monotonically with increase in p minus 1 of 0, that is 1. And the second point is that below a certain threshold, okay, more precisely, when p minus 1 0 is below a certain threshold, p minus 1 L goes to 0 as the number of iterations increases. All right. As an example, when dV dC equal to 3, 6, then your design rate satisfies k by n is greater than or equal to 1 minus 3 by 6, which is 1/2, and the threshold observed here and the threshold exhibited by Gallagher decoding algorithm A is is crossover probability equal to 0.04, which means that provided the crossover probability is less than 0.04, you will actually make error free decisions. However, this is a relatively simple decoding algorithm. So you shouldn't expect too much out of it. So just make a quick note that in comparison, channel capacity dictates we should be able to operate provided epsilon is less than 0.11. Okay. Now, okay, so that finishes our analysis of Galler decoding algorithm A. What I'd like to do next is again go back to our last lecture and prove something that we had left unfinished last time, namely the proof of this particular statement. Okay, so we will now proceed to show. So this was carried over from last time, that the number of incorrect messages passed along the edges of the Tanner graph during each iteration is independent of the transmitted code word. Okay, so this was earlier deferred to this. So let's remove this. Okay. Let's show how we do that, and I'm going to actually pick up a couple of pictures from the last lecture. So we had this picture here for messages. As well as this one. Now, I'm also going to draw one additional picture here, and I'm going to make this rather quick. or at least I am going to try to make it rather quick. Now, so the idea is to actually show that, let us say that the channel realization is fixed and we allow the code words to vary, and we want to show that the number of incorrect messages edge by edge, iteration by iteration remains the same, and therefore, without loss of generality and for the sake of convenience, we can actually assume that the all one code word is actually transmitted. Okay, so, for that I am going to make a slight detour first and talk a little bit about the channel. Now, let us assume now we had a channel. If you recall earlier, when I actually talked about the channel, we made the following assumption, which I called at that time the channel symmetry assumption, which basically said that the probability of yt given xt was equal to the probability of minus yt given minus xt. Okay. So, here I am thinking of the following picture, that is, the input to the channel is xt and the output is yt. Now, and your xt here is either plus or minus 1. Now, let us define. So, define here yt equal to xt zt. So, in other words, I am going to define zt as yt divided by xt. Now, I am always free to do this. I am always free to actually do this. And now, what I want to actually show is that we will now show that xt is independent of zt. What does that mean? It means that you can actually view the output of the channel as taking something that purely comes out of the channel and multiplying it by the input. So, it is a nice and simple, because there is no coupling between these two, that is, zt is not dependent on xt. So, we are just going to make use of this particular equation. So, let me call that 4. Okay. So, P of let us say P of z given x of zt given xt, okay, is the same as P of now let us say that we condition this upon xt equal to 1. Now, if the probability when xt is equal to 1 of z being equal to zt is the same as the probability y equal to zt given xt equal to 1. Okay. So, we will write that as P of y given x of zt given xt is equal to 1. Now, P of z given x zt given xt equal to minus 1 is P of y given x, and this time, since xt is minus 1, this yt is equal to minus zt. So, this is the probability of minus zt given xt equal to minus 1, but by the channel symmetry condition, this is the same as P of y given x of zt given xt equal to 1. Okay. So, this is by equation 4, which was our channel symmetry condition. So, what that means is that the probability of ZT does not depend upon whether XT is plus or minus 1, okay. Therefore, it is independent. Therefore, P of Z given X, ZT given XT is simply a P of Z ZT. It is independent of thing. Okay, so, that is one thing to keep in mind. So, at the end of all that, we have a very simple picture of the channel, namely that what the channel does is it takes whatever the input is, that is under the channel symmetry assumption, it takes whatever the input is, multiplies it by a certain random variable ZT and sends it out. So, now we want to actually say that the number of incorrect messages remains the same. So, here consider that your YT is your incoming message, perhaps I should write them in red. So, the incoming message is YT, which is equal to XT into ZT. Now, what does Gallagher's now let us we assume in our variable node map, I think we defined that perhaps in some point in our last lecture, that is that here when we so these we called, remember, the variable and check node symmetry conditions. So, let me underline that. So, I am jumping from current to past lecture, but since you will have a hard copy of this, that should not matter. So, by the variable and check node symmetry conditions, one of the assumptions was that if you multiply the input by a binary plus minus 1 symbol, that factors right out of the message. Okay. So, what that means is that here the message that is actually passed here is XT is XT times psi 0 V of ZT. That is, the message that is passed when the symbol is XT is XT times what it would have been passed had XT been equal to 1. Okay. Now, keep that in mind. So, now when we go to a check node, if we go to a check node, keep in mind that the messages that are coming in are in general XT times psi sub V of L minus 1 times the messages that they would have got otherwise. Okay. That is, this is the message with XT equal to 1. Had XT been equal to 1. So, in general what happens is that this XT keeps propagating and multiplying each message. So, the incoming messages are multiplied like this, and so let me call this actually let us say that this is x1, and then this would also be, this would be variable x1, this would be x dc minus 1 psi sub dc minus 1 L minus 1 of whatever the message would have been in the absence. Now, this should also be an incoming message. Now, what does a check node do? Check node simply takes, it says that whenever the incoming messages are multiplied by certain factors, it multiplies those factors out and sends it out. So what comes out is the product j is equal to 1 to dc minus 1 xj times the message that would have been sent out had all the messages been 1. Okay. But this thing here, this is precisely equal to x sub dc, okay, because of the parity check. That is because your parity check imposed the condition that u dc was equal to u sub j, j is equal to 1 to dc minus 1 mod 2, and your xj was minus 1 to the uj. So when you look at the parity conditions in the plus minus 1 domain, then the product of that causes the product to actually equal x dc. So what's happening here is that if your incoming messages are multiplied by the corresponding variables, then your outgoing message is also multiplied by the corresponding variable. And now when you come over here to the general case, when you are looking at excuse me, when you are looking at what happens at a variable node, the incoming message here is x1 times psi c l of whatever it would have been. Here it is x dv minus 1 times psi sub c l of whatever it would have been had xt equal to 1. We know, let us call this, so this one here is x dv times whatever the channel input message would be. Okay. So now, hold on a second, sorry, these are all x dc here. The messages are all dependent upon where they are headed. So this was x dc, this was x dc dv, this is x dv, this is x dv. So the outgoing message is also x dv times whatever the message would have been had x, all the x's been equal to 1. So as a result, what happens is that your messages are always x, the value of the variable, times whatever the message would have been had the corresponding x been equal to 1. And therefore, when you actually say incorrect, you are actually comparing the sign of x dv, the true value of x dv, with the sign of this message. But that is just like comparing this against whether this is 1 or minus 1. Okay. So therefore, for this reason, the number of incorrect messages is independent of the transmitted code. Okay, so I will just end with that. So we have about 2 minutes left. So let me just summarize what we did today. So basically what I did was I completed our computation of density evolution with respect to Gallagher decoding algorithm A. I tried to clarify a few things which I thought were not clear last time, and then we went ahead and proved the statement that I had made last time, that the number of incorrect messages is independent of the transmitted code word, and therefore you are free to assume in the analysis that the transmitted code word is all a 1. Okay, that fills a hole in our development of the theory from last time. So what lies ahead? So next time what we will actually do is that we will actually look at, now we looked at one decoding algorithm, this is Gallagher decoding algorithm A. Next time we will actually look at an algorithm which is called the belief propagation algorithm. It sounds fancy, but all that we are really doing is basically using the message passing algorithm that we developed using the GDL and the junction trees. Okay. So I will catch up with you on the next class. Thank you.